Hi friends, here is a nice problem. We are given this function f of x equal to x by 1 plus absolute value of x. Now when is this differentiable? Right, differentiable means firstly this function should be continuous. It should be continuous, it should be smooth. That's what we have discussed. Right, we should not have cusps like this or corners like this. So where from two different directions we are getting two different slopes. That should not happen. Then the function is differentiable as long as it is continuous and smooth. Right, x by 1 plus absolute value of x. So firstly, please note the denominator will always be positive because the absolute value of x is always greater than or equal to 0. So there is no question of denominator becoming 0. X cannot be 1 minus 1 cannot happen, right? Because the absolute value of x is always positive, right? The lowest 1 plus mod x or absolute value of x, the lowest it can become is 1 when absolute value of x becomes 0. Right? Denominator is never negative. So there are no vertical asymptotes. Right. Now the only thing that we have to worry, because denominator is never negative, so this function is generally continuous. Probably at x equal to 0, this will become x by 1 minus x when x less than 0, x by 1 plus x when x greater than or equal to 0. So we have to worry, we have to check it when x equal to 0 whether this function is continuous and differentiable or not. Okay, so first let's go by the formal way also, then we'll go by the informal way and see whether the graph also is making sense or not. Okay, x by 1 minus x. Okay, we have to verify whether it is continuous or not. First of all, left side, right side, we are still getting both sides, we are getting 0. So that's why it is continuous, whether it is differentiable or not. So what is the derivative of this function? Derivative of function at x naught is f of x naught plus h minus f of x naught by h when limit h tends to 0. Right, this is the definition of derivative. What is x naught? X naught is 0. So basically f of 0 plus h, that is nothing but f of h minus f of 0. What is f of 0? F of 0 is anyway 0. F of h minus 0 by h and limit h tends to 0. Right. So now we have these two functions. Let's do this limit when h tends to 0 plus and 0 minus also. So limit h tends to 0 plus. 0 plus means from the right side of 0. Then that is this one. Right. What is f of h? H by 1 plus h whole of this by h. Right. And this h will get cancelled. So we can directly substitute 0. This becomes 1. Now what will happen when we do limit h tends to minus 0 minus? Then this becomes h by 1 minus h by 1 minus h whole of this by h again, f of h minus 0, right? So again here also will get cancelled, we'll be left with 1 by 1 minus h, which is nothing but 1 by n minus 0, which is nothing but 1. So at 0, firstly this function is continuous because both are zeros. At the same time, the slope from the left hand side and right hand side both are coming equal to 1. So that's why this is differentiable at 0 also. At all other places this function is anyway continuous. So x by 1 plus x, right? X by 1 plus x is a very continuous function, right? So that's why it is differentiable at all places. Now let us understand little bit more about this function. Right, let x by 1 plus x and x by 1 minus x. We have two parts, right? So this is a rational function, right? What is a rational function? Rational function is ratio of polynomials, p of x by q of x. Both should be polynomials, right? Now here the polynomials, both of them are of the same degree 1, right? Both are linear equations, x by 1 plus x. Now we have to draw, when we want to draw graphs of rational polynomials, what we have to check? We have to check for zeros. That means when this let's say if we call f of x equal to this, when the function is 0, that means when the numerator is 0, when the denominator is 0, that is some vertical asymptotes and any horizontal / oblique asymptotes. Right, oblique means / asymptotes. Right, we have to check for asymptotes basically, and we have to check for zeros. Zeros are the places where the function touches x-axis, and asymptotes are the places where we have to take care vertical and horizontal. Horizontal asymptotes, right? Vertical asymptote we have to show something like this, and horizontal asymptote will show something like this. Okay, something like this or something like this. We have to show the curves properly. Now, this function we already discussed when the degree of numerator and denominator is same. That means highest power of x and highest power of x and both numerators are same. Then the horizontal asymptote is the ratio of coefficients of this and this, numerator and denominator. Here it is in this case 1 by 1. If the function is x by 1 plus x. For example, if the function is x cubed plus 3x square plus some x plus some constant by again 4x cubed plus again some x square, some x, some constant something. Because highest power is x cube, highest power is x cube here. The horizontal asymptote would be coefficients of this, ratios of coefficients of this, which is nothing but 1 by 4. Here highest powers are 1 and 1, x power 1 and x power 1, and coefficients are again 1 and 1. So y equal to 1 is a horizontal asymptote. Right. And in this case, x plus 1 will be 0 when x equal to minus 1. So at minus 1, there will be vertical asymptote. Right. If you have to draw this graph, then it will look something like this. Okay. This green one, there is a vertical asymptote at x equal to minus 1. See? So it will look something like this. At x equal to minus 1, x equal to minus 1. So this line is a vertical asymptote. Okay. For this graph. And at the same time, this graph has a 0 at origin. Right. This graph has a 0 at origin because numerator is 0. So it has to pass through origin. And at the same time, there is a horizontal asymptote at y equal to 1. So basically, the graph is simple. It is like this and like this. That is a horizontal asymptote. That is a vertical asymptote. Vertical is when x equal to minus 1. Horizontal is when y equal to 1. Okay, so that's what we have figured out. The graph is actually the green graph. Now this green graph is applicable when x is greater than or equal to 0. So we will take this part of green graph. Right, only when x is greater than 0. Right, x by x plus 1, x by 1 plus x when x is greater than or equal to 0. And x by 1 minus x when x is less than 0. Now let's try to draw this graph x by 1 minus x. Here, what is the horizontal asymptote? 1 by minus 1, coefficient of highest power of x 1 by coefficient of highest power of x 1 by minus 1, which is minus 1. So obviously, this minus 1, there is a horizontal asymptote. Right. And when is the vertical asymptote? When x equal to 1. The denominator becomes 0. That is this one. That is this one. So the graph is again, it looks similar. Sorry. Okay. So again, at x equal to 1, there is a vertical asymptote. X equal to minus 1, y equal to minus 1, there is a horizontal asymptote. So the graph is something like this. Okay. Sorry, the graph is the reverse of this. Okay, so the graph goes through 0. Right, the graph has to go through 0 also. Where is the 0? When x equal to 0, this is the 0. The graph has to go through 0 and there is a horizontal asymptote. Right, it has to go through 0. It should approach x equal to y equal to minus 1 and it should approach x equal to 1. Right. So it should approach this line also. It should approach this line also and it has to go through 0 also. Right, it has to go through 0, 0 also. Right, if this is x-axis and y-axis, it has to go through 0, 0 and it has to approach the one vertical line and one horizontal line. So this graph x by 1 minus x is this red line. Now this we have to take, it is applicable for x less than 0. So what is our overall graph? Overall graph is this entire blue one, green one on the right side and red one on the left side. Basically, we are taking half of graphs of both red one and green one. Green one on the right side of 0, and red one on the left side of 0. So this graph is actually very smooth, right? We have just calculated that at this point 0, the slope is actually equal to 1 in both places, whether you approach from right hand side or left hand side. The slope is actually equal to 1. We have just calculated that. So that's why this graph is actually smooth. It is very smooth at 0 also, and it is smooth elsewhere also, right? And that's why it is always differentiable. It is continuous, it is smooth, so that's why it is differentiable everywhere, right guys? So please note, when we are getting horizontal asymptote and vertical asymptote, so we have to be careful whether we draw graphs like this. So we'll get two sets, right? Two sets of graphs. This is one kind of set, or we'll get a second kind of set like this. We have to be careful. We have to be careful whether you are choosing this one and this one, or this one and this one. How do we choose this? Let's take one random x. Right. So for example, we are talking about x by 1 plus x. X by 1 plus x. When x becomes very large, so obviously x is always lesser than 1 plus x. Let's say for example 100 by 101. So this number will keep getting closer to 1, but it will never reach 1. So that's why we are approaching this horizontal asymptote from the bottom. That means it is becoming 0.9, 0.99, 0.999, whatever. So that's why this graph is actually from the bottom, right? This graph, when x is very large, this graph actually will try to approach it from the bottom, right? Similarly, if we take this one, x by 1 minus x, when x becomes very large, it becomes 100 by 1 minus 100, which is roughly minus 1.9. So this also is slightly greater than slightly lesser than minus 1, right? So that's why it is also approaching from the bottom of minus 1, right? It is trying to approach this one, right? Yes, that's how we can say whether we'll choose this and this, or we'll choose this and this. You have to be little careful in choosing the right ones. Or at the same time, we can choose where origin is falling, whether in which of the sets. In this set, origin is falling, or in this set, origin is falling, or in this set, or in this set. That's how we can easily say which two lines we are picking. Right. This is how we draw graphs of rational functions. Very easy. First, we have to see where are the zeros. That means where are the numerator zeros of a function, and where are the denominator zeros. That means where are vertical asymptotes. Zeros means when they are touching x-axis. Vertical asymptotes means when the graph will go to infinite, plus infinite, minus infinite, and horizontal axis, horizontal asymptote, when x tends to plus infinity or minus infinity, how will the graph behave, whether horizontal asymptote or oblique asymptote. Oblique asymptote, when do we get? When the highest power of numerator is 1 higher than the denominator. So for example, 3x cube plus 4x square plus something plus 2x plus 7 whatever, by again 5x square plus 7x something plus 8 whatever, right? Here highest power of x here, x cube, is 1 more than highest power of x here, right? In this case we will get an oblique asymptote. Okay, so earlier we had discussed in other places. Please go through that video to find out how to find the oblique asymptote also. Right guys, hope you like this. Thank you. So in this problem, so finally what is our solution? Our solution is, it is differentiable everywhere. Right guys? Thank you.